前回投稿の補足。人間や生物は生命発現と同時に自発性と自意識が付与され、生命消失と同時にこの大自然に還る。人間は生命発現と同時に自発性と自意識が付与され、生命消失と同時に自発性と自意識を失う。今回の投稿は12月22日に投稿した意識成立の科学的説明が不能なのは今の物質科学が不完全だから云々の補足版であり、ぜひとも補足しなければならない事項がある。前回の投稿では人間や一般社会が持つ生物の死生観は間違っており、生物の個々の生命活動は量子力学的な非局所性によって可能になると述べた。人間が生物個体として駆動できるのは、この世界に量子力学の正規論あるいは半神論のような生命を躍動させるエネルギー相対あるいは自然全体の躍動エネルギーが供給源であり、この時点で人間には生命発現と同時に自発性と自意識が自然から付与され、他の個体との区別ができると述べた。では、人間や生物の死についてはどうかというと、生命消失と同時に自発性と自意識を失うから、死亡した生物の死体が物質としてそこにあっても、そこに供給されていた生命エネルギーは量として減ることもなく、死亡した生物に供給されていた生命エネルギーは自己という特段の区画はなくなり、新生回帰として新たに誕生してくる生命エネルギーとして自然に還元され供給される。言葉を返せば、生命誕生と同時に自発性と自意識が自然から付与されるのは、他の個体との区別のために必然なことである。この生物の個別性については、魚類に見られるように、大型捕食種であるクジラなどが、小型のイワシなどを大量に捕食するときに、自然な躍動と思われるが、イワシの集団が一時的に個別性を弱めて共同運動をとるような姿が見られる。クジラのような大型捕食種から逃げるのなら、バラバラで逃げた方が捕食されないようにも思えるが、捕食から逃げるだけが目的ではないのかもしれない。また、渡り鳥が集団行動をとるのは、目的地まで迷わないことが大きいのだろう。人間の通常生活に注目したとき、覚醒と睡眠サイクルで、睡眠は人間の自発性と自意識をかなり減弱または消失させるが、他からのかなり小さな刺激でも、瞬時に意識を回復して物事に対応することができる。その場合の脳科学からの説明は確立しているのだろうか。また、麻酔薬を用いた大手術では自発呼吸も停止するので、人工呼吸器も用意する必要がある。この麻酔薬による脳の麻酔作用について、まだ未解明の部分があると言われるが、投稿者は、その詳細がどのようなことなのかは知らない。ただ、ロジャー・ペンローズ氏と共に、意識成立の研究に携わられているハメロフ氏が麻酔科医というのも、偶然ではないようだ。以降の映像は、意識成立の研究にも携わられているロジャー・ペンローズ今日の公開説明会の映像である。この映像はクリエイティブコモンズが宣言されているので、投稿者も使用させていただきました。
Hello and welcome to this afternoon's debate, which looks as if it's going to be absolutely fascinating. The mystery of the multiverse. Multiverses are everywhere, or at least the theory is. Everyone from physicists Stephen Hawking and Brian Greene to Marvel superheroes have shown their support for the idea. But critics argue that not only is the multiverse improbable, it's also a fantasy and fundamentally unscientific, as the theory can never be tested. Should we reject the grand claims and leave multiverse theories to the pages of comic books? Are tales of the multiverse really sticking plaster solutions for a Big Bang theory in trouble? Or should we take multiverse theory as seriously as its proponents and accept that modern science has moved beyond the bounds of experiment into that of the imagination? So with me to discuss the topic, a remarkable panel. Michio Kaku is a leading string theorist and one of the founders of string field theory. He's written a host of best-selling books, including The God Equation and Parallel Worlds. Sabine Hossenfelder specializes in the foundation of physics. She's a research fellow at the Frankfurt Institute for Advanced Studies and leads the superfluid and dark matter team. And Roger Penrose, who needs no introduction, is a world-renowned mathematician, physicist, and philosopher of science. He was awarded the Nobel Prize in 2020 for his work on black holes. So I'm going to give each of them just 3 minutes to address the central question, which is, does the multiverse exist, or should we reject the grand claims and leave the theory to science fiction? So, Michio, it's all yours.
Thank you very much. Well, the most successful physical theory of all time is called the quantum theory, and it's accurate to within 1 part in 10 billion. And the world economy is based on the quantum principle. Lasers, the internet, this conversation is made possible because of the quantum theory. But the quantum theory is based on a strange principle, that electrons can be two places at the same time. Now, Einstein hated that principle. He once said that the more successful the quantum theory becomes, the sillier it looks. Well, sorry about that, Albert. But it turns out that the world economy is based on the fact that electrons can be in multiple states at the same time until you measure it. Now let's apply this theory to Einstein's theory. Einstein says that the universe is a bubble of some sort, which is expanding. That's called the Big Bang theory. But if this is correct and we quantize the universe, then the universe can be in multiple states at the same time. In other words, instead of a bubble, it's a bubble bath. And these bubbles can collide. And when they collide, they form a bigger bubble. Or a bubble can fission in half to create two smaller bubbles. And what is that called? That's called the Big Bang. And how do you prove it? Well, so far the data seems to go in the favor of inflationary theory. And inflationary theory in turn is based on the idea that universes are being born all the time. Even as we speak, Big Bangs have been happening someplace in this great universe of ours. And then where does inflation theory come from? Well, one theory that seems to predict inflation theory is called string theory, which is what I do for a living. And if I have time later, I'll talk more about it. But then the question is, how do we visualize these higher dimensions? Well, Nobel laureate Steve Weinberg gave us a way to visualize these higher dimensions. Think of your living room. In your living room, there are hundreds of radio signals from radio stations all over the world in your living room. But your radio has decohered. It's not tuned. It's not tuned to the radio stations. Your radio is only tuned to one frequency. Now replace radio with electrons. Your living room is full of electrons. The electrons of pirates, dinosaurs, aliens from other star systems, all in your living room, but you are no longer vibrating in phase with them, says Steve Weinberg. In other words, yes, there is a multiverse of universes out there, but the probability of entering them, of being coherent with them, is too small to be measured. One problem we give our PhD students is calculate the probability you'll wake up on Mars tomorrow. Well, it's a finite number. You can calculate it. But tomorrow, I suspect you will wind up in your bedroom. You will have to wait a time with the universe to wake up on Mars. But is it possible? Well, yeah. And that's what separates physics from Marvel comics. Marvel comics, all these feats of imagination are for free. In real physics, we can calculate the probabilities of these things happening, and you will have to wait longer than the time of the universe. Sorry about that, Spider-Man.
Thank you, Michio. So, Sabina.
So I think that all those multiverse theories which we have seen popping up in the foundations of physics come from the same misunderstanding, which is that we have physicists who come to believe that the mathematics that they deal with is actually real. So typically the way that it happens is that they have a theory which makes some predictions that agree with observations, and they take that to mean that because some of the things that they can predict agree with observations, all the mathematics that is in their theory has to be real. And to me that's completely insane. That's like saying, okay, so Harry Potter goes to King's Cross Station, which is a real place, therefore magic is real. That's just not a good logical argument. But I think it's a little bit a false dichotomy to say, well, it's either science or it belongs into comic books. There are some things in between. So I think multiverse theories have some value as being philosophical speculations, or maybe some people find them inspiring. They have certainly inspired a lot of artists, writers, and so on, and I think there's value in that. Also, I think one has to keep in mind that even though they're not testable at the moment, maybe sometime in the future they will become testable. So for most of those multiverses, the reason we can't experimentally access them is that nothing travels faster than the speed of light, for all we currently know. So maybe at some point in the future that we will be able to overcome the speed of light limit, in which case multiverses might actually become testable.
Thank you, Sabina. Roger.
Well, I had a bit of trouble when I saw the topic of this meeting, not really knowing what people meant by the multiverse. I think many of the alternatives that I've come across, I would use up all my time trying to distinguish between them. I think I'll comment mainly on what Mikio was talking about, namely quantum mechanics, and the issue that in quantum mechanics you seem to have to consider all sorts of alternative things which happen simultaneously. Now the trouble here is the theory, in my view, it may well be, as mentioned earlier, the most successful theory we've ever had. The trouble is it may be successful, but it's not really consistent with itself. The trouble is it consists of two parts. One of them is what one can call the Schrödinger equation, how the quantum state evolves in time, and the other has to do with what happens when we make a measurement. And the two things are inconsistent, because if you imagine making a measurement, then that involves a measuring device, and that seems to come in from outside. The measuring device is not considered to be a quantum system itself. If it is, then it doesn't measure anything. So I have a real trouble with quantum mechanics for this sort of reason. It is clearly a successful theory. It clearly has enormous implications that we see agree with the physical world. However, it has this big blemish. It was quite pointed out by Schrödinger himself. He described this thing in his hypothetical cat, which was dead and alive at the same time. And he was more or less not saying, as some people say, well, maybe if you're clever enough you could build a Schrödinger's cat which was dead alive at the same time. Schrödinger was pointing out the absurdity of the situation, more or less to say there is something wrong with the theory. And that's my view, is that there is something wrong with the theory, even though it is such a wonderful theory. What's wrong with the theory has to do with superpositions which are not just, say, electrons and here at the same time, but big bodies which are here and here at the same time. And in my opinion, if one considers the foundational principles of the other great theory of 20th century physics, namely Einstein's general theory of relativity, you realize that there are issues of conflict between the general principles of general relativity and those of quantum mechanics. And in my view, that it's not just that general relativity has to be quantized, in other words, brought under the general scheme of quantum mechanics, that quantum mechanics needs help itself. And the help it needs is to get rid of all these different alternatives. One thing happens, not the superposition of all the different things. And one can understand that by exploring how general relativity relates to macroscopic superpositions. Now, I'm not going to go into that here. It's not the place to talk about it. But the conclusion one seems to come to is that when you have a big enough body, which is in the superposition of two places, it has a lifetime in that state which very rapidly becomes one or the other. And a theory which improves upon quantum mechanics brings in general relativity in the right way. It's not quantizing general relativity, which people often say is the major problem of physics, if you like. It's gravitizing quantum mechanics. We have to see what happens when the principles of general relativity are brought to bear on quantum mechanics, and then you see that you don't have all these superpositions of different things at once. You can have one thing or another. The bigger the thing is, the more rapidly it becomes one or the other in a perfectly coherent scheme. Now, I'm afraid that at the moment we do not have a complete theory of this nature. I regard it as the biggest challenge of current physics, to see how to bring these theories together and to rid quantum mechanics of this big blemish, namely the measurement problem, or the fact that superpositions seem to be present in quantum mechanics, and really we want a theory which has one alternative or the other persisting for macroscopic bodies.
Thank you, Roger. So before embarking on talking about a number of different themes we are wanting to explore with the panel, I'd just like to get a little bit clearer the question that Roger sort of posed there, that the multiverse is used to refer to all sorts of things, very different sorts of multiverse, where there are some claim there are infinite universes other than our own, and there are different versions of this. So I think just briefly to try and get clear what the different positions are of those on the panel here. So, Michio, I understand you as arguing that there are an infinite number of other universes with potentially different laws than this one. Is that correct?
Yes. String theory, for example, probably has an uncountable number of infinite universes. And of course, that begs the question. People often ask me, well, if that's true, then is Elvis Presley still alive in one of these parallel universes? Well, it can't be ruled out. Maybe he's still belting out his hits in another parallel universe. But let me make a challenge to everyone in the audience. We're dancing around the question, is there a theory of everything which can unify general relativity with quantum mechanics? Let me give you a challenge. If anyone in the audience can come up with a theory that satisfies three criterion, you'll probably be recognized as the next Einstein. First, your theory has to include general relativity, at least in the low energy realm, general relativity. Second, it has to include the standard model with, of course, 36 quarks and anti-quarks, 3 generations of subatomic particles, and a whole slew of Yang-Mills particles. It has to include the standard model. And 3, your theory has to be free of anomalies and divergences and mathematical inconsistency. And if you in the audience ever find this table theory, then tell me first.
Well, yes. we'll try and come to your rescue, Monsieur.
We'll split the Nobel Prize money together. You and I.
Yeah, very good. So, Roger, sometimes I think your view is described as a multiverse, but it's a cyclical multiverse. It's the idea that this universe did have something before the Big Bang, and there was a previous universe, and that in fact if you look back indefinitely there are a whole series of expansions and contractions going on in sequence. Is that right? And would you describe that as a multiverse, or do you think actually you really see that as one universe, it's just that it goes through a series of stages?
It's certainly only one universe. There's no multi-universe about it. And it doesn't contract, I should say, but never mind about that issue.
Yeah.
No, the point of view, that's completely different, of course, to what I was talking about
Yes.
now, was the issue of the quantum mechanical, apparently multitudes of different things.
Yep.
But yes, what you're pointing out is this model which I put forward some years ago, where you have a sequence of phases, or eons as I call them, but they're all part of one universe. Moreover, things which happen in the one before ours influence ours in ways which are observationally testable. And some of these have been tested, and we see positive conclusions from these things. So I don't regard this really as being, as you were saying, suggesting, I think, that this is not a multiverse in any normal I don't know, is there a normal sense of the word multiverse? But it isn't one in the sense that I've heard expressed here.
Thank you, Ron.
Yeah.
So, Sabina, let's come on there, the first theme I'd like to put to the panel, which is, do scientific theories have to be testable? And does multiverse theory threaten this basic principle?
Yes and yes. But maybe let me expand a little bit on this. I actually don't know anyone who works on multiverse stuff, or generally in the foundations of physics, who would question that theories have to be testable. Rather, what's going on is a little bit more subtle. There are three different arguments that people make about testability in the foundations. One is that the theory may just not be testable yet. That's typically an argument that string theorists make. So in principle, it makes some predictions, but we would have to build a collider the size of the Milky Way to test it. So maybe one day we'll be able to do it, but not anytime soon. The second one is a switch and bait tactic, where they switch the overall principle, that could be the multiverse, or it could be dark matter, or theory of everything or something, for a very specific model. So you have this overarching idea like the multiverse, and someone comes and says, well, it's not testable. Then they can say, well, I have this very particular model for the multiverse, which makes a particular prediction. For example, there are some multiverses in which the universes can collide, basically, and it leaves a signature in the cosmic microwave background, which is something that you can look for. But then if someone goes and looks and doesn't find it, they say, oh, it was only this particular version of the multiverse that has been ruled out. We still believe that the overall idea of the multiverse is correct, and it's the same for dark matter particles. So basically you can indefinitely amend your theories whenever there's conflicting evidence coming in. You go back and say, well, here's a different model.
Okay,
and then
let me put that. Shall I put that to Michio and come back to you?
Can I just finish the third
Yes,
one? Otherwise,
always,
I'll forget about it. The third one is the argument which I briefly mentioned in the beginning already, that they say, well, actually, I have a theory that does make some testable predictions and that have been tested. Therefore, I also believe that all the other mathematics is real, even though you can't test it.
I see. Thank you. So, Michio, science needs to be testable, and your theory isn't.
My theory, that is string theory, is testable in 4 different categories of experiments. Experiment number 1. The Fermi Laboratory has for the first time in history found an anomalous behavior in the magnetic moment of the muon, which indicates a new force outside the standard model. This is huge. It means that quantum physics is being shaken to the core if the result holds up with Fermi Laboratory, a deviation in the standard model. Number 2, dark matter. Dark matter will collide with protons, leaving a spark in a spark chamber, which in turn can be measured and then compared against the different dark matter predictions of string theory, like the photino. The photino is a particle in string theory which has no charge, is massive, and obeys all the properties of dark matter. And it could be found any day in a spark chamber. 3, deviations from Newton's inverse square law. We know the universe is three-dimensional because, as we learned in grade school, gravity diminishes as the inverse square. But what about the inverse cube, the inverse quartic, the inverse quintic? If the universe has a higher dimension, then gravity should taper off in the laboratory, not in outer space, in your laboratory faster than usual. Number 4, eventually the ESA and NASA will launch LISA into outer space. LISA is a laser interferometry space antenna designed to pick up radiation from a trillionth of a second after the instant of the Big Bang. In other words, we hope to get baby pictures from the infant universe as it emerges from the womb. And hopefully, this is, of course, keep your fingers crossed, hopefully we'll pick up evidence of an umbilical cord that connects our universe with a baby universe. And again, all 4 of these things do not require a particle accelerator the size of the Milky Way galaxy. These results are coming in now, even as we speak. Results from Fermilab, results about dark matter, and discussions of the inverse square law. These are things that can be done in our lifetime. And even then, we're not talking about direct measurement of these things. We're talking about indirect measurement. We have never been to the sun. We have never been inside a DNA molecule. But how do we know so much about the sun? Have we been there? No. Have we been inside a DNA molecule? No. We know that by indirect analysis. Most of physics is done indirectly. So it's a false scarecrow to introduce the idea that you have to have a particle accelerator the size of the Milky Way galaxy. That's a direct confirmation of string theory. I'm talking about the same way we know so much about the sun and so much about DNA molecules by indirect measurements, which lends us to believe that string theory is correct.
So I'll just ask Sabina to respond to you in a moment. But initially, you pointed to lots of questions that there are about our current theories of the universe. You know, dark matter, the recent muon experiment, and so forth. But can you really point to those as evidence of the multiverse theory? I mean, aren't there lots of other possible accounts of that? And indeed, they remain deep puzzles. But you know, the fact there are deep puzzles with our current measurements of various things doesn't show us that the multiverse theory has been proved to be the case, does it?
Well, there are degrees of confirmation. In other words, to have a theory completely confirmed takes a lot of time. Look at the atomic theory. How long did it take for us to confirm Democritus' conjecture 2,000 years ago that there's such a thing as atoms? It took 2,000 years before we had the first clear pictures of atoms. But in between then, we had plenty of indirect measurements, plenty of indirect theories that indicated that, yes, atoms were real. Same thing with multiverse. It'll take time to get all the facts in place, but all the facts so far point in the direction of the multiverse.
Okay, thank you. So Sabina, we might not have direct evidence, but we might have indirect evidence, and the parallel with the collider the size of the Milky Way is misleading.
Well, so the observations, the potential observations that Mishu just mentioned, if they were found, they would not be evidence for string theory. It's just wrong. I know a lot of string theorists, serious string theorists, and I think none of them would make that claim. And I can explain this in great detail, but it would take a long time. Maybe I'll just take an example. Deviations from Newton's square law. This is something that people have looked for a long time. There are many ways to explain them. Could be an additional new force, could be additional dimensions, but it's got nothing to do with strings. It's certainly the case that there have been some predictions inspired by string theory, which would also lead to these deviations, but we face what's called the inverse problem. We have, maybe one day we will have some observations, and we try to infer what the theory was that gave rise to them. And this is just completely underdetermined, as the philosophers put it. There's no way to get out string theory in particular.
Do you want to respond to that, Mishu?
Well, as I mentioned before, it took 2,000 years to completely verify the atomic theory. Now we have pictures taken from scanning tunneling microscopes But in between, there were many partial results that gave us indirect proof of the existence of atoms. Einstein in 1905 was able to show, using statistical mechanics, that atoms were probably the size that we think they are today, 10 to the minus 8 centimeters. And it took time. And so I think not in one flash we're going to prove that the multiverse theory is correct or that string theory is correct, but the overwhelming weight of evidence will point in that direction. And let me make another challenge to everybody in this room. You are free to not like any of these theories, but if you don't like these theories, propose your own. The second law of thermodynamics says that it's always more difficult to create a theory than to destroy a theory. You can dislike any of these theories that we talked about today, but I challenge you, come up with a better one.
Well, there's an excellent opportunity to introduce Roger into this conversation.
Well, I'm not a particle physicist, so I don't claim to have a better theory than string theory, although I'm pretty disappointed by the conclusions. I mean, just to mention how other theories have taken a long time to confirm and so on, tells me nothing about string theory. I mean, string theory proposes the wrong number of dimensions of space, for instance. It proposes the wrong sign for the cosmological constant, for instance. All sorts of things which have come out of string theory are just wrong. Now, you could get round this one way or another. I know people like to tuck all these extra dimensions into a little tiny ball. They haven't answered the question that I've often raised in my books about that, which is that it doesn't really solve the problem. I mean, there are big, huge problems facing string theory. I don't quite know why we're talking about this with the multiverse anyway, because string theory is a particular theory which I don't think has much in the way of support for it. It's got a lot of people who argue for it, but that's not scientific support. There aren't experiments which support string theory. But that's really a different question from the multiverse, isn't it? Are we talking about string theory or the multiverse here? I'm not sure.
Well, both. String theory has been criticized for being a multiverse theory.
Oh.
But I don't mind, because even if you take a look at Newton's laws of motion, they are also in some sense a theory with an infinite number of possible solutions. If string theory has an infinite number of solutions, well, so does Newton's laws, Maxwell's equations. They all have an infinite number of solutions, but how do you make sense of it? By looking at the initial conditions. That's how you can prove that Newton's theory is correct, by starting with a baseball, starting with a rocket. Same thing with string theory. You start with the initial conditions of the universe, and then you can project into the future. The problem is experimental. We do not know the initial conditions of the universe. Therefore, we cannot directly compare it to a multiverse theory. But that's an experimental question, which I think will be answered as we have more and more satellites detect things like gravity waves in outer space.
Mishu, some people would say that what we need to do when we're proposing theories is to apply good ancient philosophical principle of Occam's razor, that you generate as few new entities as possible. But the proposal that there's an infinite number of other universes seems on the surface it to rather break that principle. Do you not think that a more modest proposal might be more comfortable?
People have tried. People have tried for decades to tear apart the multiverse theory. But as I mentioned, it's a legitimate interpretation of quantum mechanics. It agrees with all the experiments. Now, there are other interpretations of quantum mechanics. You don't have to believe in the multiverse theory to get 10 billion, 1 part in 10 billion accuracy for an experiment. There are other interpretations of quantum mechanics. But the multiverse interpretation is the cleanest, simplest interpretation, because you simply drop one of the postulates of quantum theory. So the multiverse theory is actually simpler than the quantum mechanics that I teach at City University of New York. By dropping the postulate that you make an observation and the wave function collapses, you actually simplify quantum mechanics.
Would you agree?
No. No, I don't understand all that. I mean, you've got to... the idea is I mean, this is the many worlds. What's that got to do with the other things? There's so many things which seem to be brought in relation to the multiverse that I'm really confused about what's being talked about. I mean, quantum mechanics, yes. If you don't have the collapse going on in quantum mechanics, you have all these superpositions going on which we don't see in the world. Something you've got to do about that. But what's that got to do with the multiverse? Just postulating that they're all there doesn't help. And that's a different multiverse. Anyway, it's not the multiverse where I don't know. I really get very confused about how these problems are resolved by having a multiverse. It doesn't to me help anything.
Okay, let me move on to our next theme here, which is if experimental evidence for the multiverse is at least short on the ground, if not impossible, what's driving the multiverse story? Is it because Big Bang theory is in trouble and we need something to solve that? Is that what's driving it? Sabina?
Well, so to some extent that's a sociological question about why do physicists do what they do, but maybe it's worth saying a little bit more about the question about the Big Bang theory being in trouble. I can only guess what Michio was referring to when he was talking about the gravitational waves in the early universe. I suppose it was the B modes in the CMB, is that right?
No.
No?
I'm talking about a future generation of space-based gravity wave detectors like LISA, Laser Interferometry Space Antenna, being pushed by the European Space Agency and NASA.
Yeah, but what's the signal? Primordial gravitational waves.
That's right. Gravitational waves before 300,000 years after the Big Bang, at the instant of creation itself.
Yeah, right. So why would this be evidence for the multiverse? I suppose because you say it would be evidence for a particular type of inflation. Is that the idea?
No, because once you have data from a trillionth of a second after the Big Bang, you can run the videotape backwards and see what alternate universes a trillionth of a second before the Big Bang match the data a trillionth of a second after the Big Bang. And so in other words, in this sense, we can actually get data from before creation itself, from before t is equal to 0, by extrapolating post-Big Bang radiation to the pre-Big Bang era. And then, of course, string theory gives you a number of predictions about the pre-Big Bang universe. That's what string theory does. It gives you finite results for everything. And so you can actually calculate the pre-Big Bang radiation and compare it with the post-Big Bang radiation of gravity, space-based gravity wave detectors.
Yeah, but what's it got to do with the multiverse?
Because this allows you to extract out the key universe that set everything in motion, and then you know which of the multiverse ideas is the correct one. Just like Newton's laws. Newton's laws has an infinite number of solutions for baseballs, rocket ships, for marbles, an infinite number of solutions. Which one is the correct one? It depends on your initial conditions. We do not know the initial conditions of the Big Bang itself. Once we have the initial conditions of the Big Bang, then you can start to rule out universes that don't match. And out of the multiverse, you can get the birth of our universe itself. So starting with the multiverse theory, you then get the theory of the universe itself by running the videotape backwards.
Well, but obviously, just to describe our own universe, we don't need all the other infinitely many universes. So,
but this would help to rule out all the other universes that do not correspond to the experiment.
Well, but
maybe let me step back a little bit. So I'm not saying that all those other universes do not exist. I'm trying to say that science can't tell us anything about whether they exist or do not exist. It's just not in the realm of science. I don't have a big problem when people talk about multiverses of whatever type, if that may be the many worlds interpretation or eternal inflation or the string theory landscape and so on. I get a problem if they say it's science, because it isn't. It's a weird kind of Platonism where scientists come to believe in the existence of mathematics.
Well, as I said, every year, as more data comes in from Fermilab, from CERN, Every year we'll have better and better data which will allow us to zero in on this theory without having to build an accelerator the size of the Milky Way galaxy. We're going to get asymptotically closer and closer, just like with the atomic theory. Every year we get more evidence of the atomic theory, even if we don't have photographs of the atom itself. Same thing with string theory. We'll get closer and closer because more data will come in, which I think will verify string theory.
But one challenge, Michio, to this proposal has been that if you make an overall proposal to account for how things are currently, as I say, you want to usually operate within the principle that it should be as simple as possible. You have argued, well, it is quite simple. I think the Occam's razor principle is you don't generate entities unnecessarily, and an infinite number of universes just breaks that principle, coach and horses. But the other people have said, well, if you are proposing something as an explanation of what there is here, but you have no evidence for it, what difference is there between a multiverse proposal and the traditional religious proposal of God, which you say, well, we can't explain everything here. We're going to propose that it's all made by something else, namely God. Isn't the idea that everything here comes from the multiverse really just a scientific version of theology?
No, I don't think so, because every time someone makes a theological statement, it stands on its own merits or whatever forever, because there's no experimental evidence supporting it. It's just pure conjecture. But as I mentioned, there are at least 4 major ways in which to verify the theory. And each one gets us closer to a complete verification of the theory, not one experiment that clinches it all at once. There's no smoking gun. But the same thing with the Big Bang Theory. There was no smoking gun for the Big Bang Theory for many decades. And so now what I'm saying is it gets us closer to truth. But religion does not get us closer to truth. It's the same. Arguments made thousands of years ago are identical to arguments that will be made thousands of years from now in religion.
Do you think, Roger, that one of the reasons that the multiverse in the version that Michio is putting forward has been proposed is because of the concern that quantum mechanics has built into it an uncertainty which Einstein was certainly uncomfortable with, and it's somehow trying to get rid of the unknownness in quantum mechanics and to say, well, we're just going to generate entities for every bit so that it's no longer unknown.
Well, if that's what it's doing, it's not very impressive. I mean, quantum mechanics has a problem, and I think that's true, despite it being the most wonderful theory we've ever had or something. It has a deep problem, but I don't quite see why that has anything to do with this multiverse issue, which has to do with string theory. I mean, there seems to be a big confusion about different concepts, different problems that people have, and calling them all the multiverse or something. I don't quite see it solves any of them, actually. I mean, Maxwell's equations have lots of solutions. Yeah, of course they do. So do Einstein's equations, so do Newton's equations. Why does that drive us in the direction of a multiverse? I just haven't got that argument at all.
And what do you think, what is driving that? I mean, it's very popular, isn't it? It sells books, sells theories, it drives science fiction. What is it about the idea of, another universe to this one that we found so appealing?
I have no idea. I don't find it appealing. Yes.
So maybe if I could say something about it. I think it depends on what we mean by popular. It's arguably popular in the popular science sense. You read popular science articles about it. People write books about it, and those books sell very well. We go to festivals and people talk about it, right? But if you look at what's actually happening in the community, in physics, there are very, very few people working on it. Like, so we have the foundations of physics, and then there's a sub-discipline of the foundations of physics where we deal with quantum gravity, and then there's a sub-discipline of the sub-discipline where there is a fringe part where people talk about the multiverse. It's not in any meaningful way popular in physics. It's just not true. So, which brings up the question, why does the general public find it so interesting? And I find this quite easy to understand. It's interesting brain gymnastics. You know, I like thinking about the possibility that there are infinitely many copies of me out there somewhere in the universe, and they're living their lives in other ways. I also like movies about it. I like it if it appears in books. You know, it makes for good fiction. And I don't necessarily have a big problem with this. I just think we shouldn't conflate the fiction with the science.
Michel, it makes for good fiction.
Well, yeah. I mean, take a look at psychology and what sells, what Hollywood themes sell, and what themes resonate throughout human history. The idea of parallel universes is not a new one. It goes back to the ancients that talked about dream worlds, that talked about hypothetical worlds. Or for that matter, look at Alice in Wonderland. The gateway to Wonderland is a wormhole. The first conceptualization of a wormhole in the English language was Through the Looking Glass by Lewis Carroll, otherwise known as Charles Dodgson, a professional mathematician at Oxford. So it's an old theme. What's new about this old theme is the fact that it now has a basis in physical reality. So far, the multiverse theory as applied to quantum mechanics, which is many worlds theory, agrees with all the data. In fact, there's no way to differentiate the Copenhagen interpretation from the many worlds interpretation. They are identical with regards to experimental verification. So you don't have to believe in the multiverse theory to be a quantum mechanical physicist, because the data from the many worlds theory and the data from the Copenhagen interpretation are identical. But when you start to talk about cosmology, and you start to talk about the universe, where it all came from, then you start to ask these philosophical questions about where did the universe come from? Is there another copy of me in another universe someplace? That's what resonates with the audience, I think, because people wonder about these things. There's a poem by Robert Frost, The Road Not Taken. And you always wonder what would have happened if I took that other road with a fork in the road. This is an internal question. And that's why it resonates with Hollywood, because now we have at least a physical theory which entertains the concept that, yes, there are many roads to reality.
Thank you, Michel. So let me just end briefly with a final theme, which is, are we always going to be in a situation where our broadest accounts of the universe have elements which are untestable?
Well, I think untestable, but in principle untestable, or just we don't have enough energy or enough money or something like that. I mean, a lot of things haven't been tested because they're pretty difficult to do. An example of that is the issue of the reduction of the state in quantum mechanics, or the collapse of the wave function. Of course, you have to have a good alternative theory of at what level do you expect to see that. And there are experiments which are proposed at the moment, some which have been performed and haven't quite got there. Maybe it'll take a long time. But these are honest experiments which will show, if they come out the way I expect actually, that there is something not quite right about quantum mechanics, and that you don't have all these other universes existing and so on. It's one thing happens. And that thing happens in a certain lifetime which you can get a good estimate for, according to some of these schemes. And it seems to me that's the way science progresses. I mean, you suggest experiments, and some of them are quite expensive, and so it takes a long time for people to get around to doing them, or they may be technically very difficult, such as the ones I'm talking about here. But does that, would this be considered to be arguments against multiverses? I mean, suppose you now a very good experiment comes up which shows that a quantum superposition does become one or the other in a certain lifetime, which maybe is predicted. Now, does that say, oh, well, we don't have to talk about multiverses anymore? Or is it really a completely different argument that's being presented here? I just feel that there's too much fuzziness, too much, well, particularly the arguments from string theory, which I don't really see.
I suppose I was wanting to ask a more general question. Is there something about the way that we put our theories together which means that there is always an element of untestability somewhere. So that, as an example of the sort of thing, I mean, so Heisenberg can certainly be interpreted as advocating the view that physics is not uncovering reality, and that's because it can't do so at some level. There's some residual element which is about the limitation of being human and making observations would mean that we can't get through to it. Another way of thinking about it would be, are there elements of science, for example, the notion that the universe is governed by laws, which is an essential idea to science, but can we really test the idea that the universe is governed by laws? Is there something that and are there therefore some essential assumptions, as it were, in any theory that we can't get at?
Well, I mean, you might say tomorrow the laws are all changed, and I mean that could happen. I don't expect it to, but I can't quite see. I mean, all the observations that have been made up to date, I mean, they tell us that the world has to be according to the physics that we understand now. I mean, just that it seems to work pretty well and very well under certain circumstances. And, I mean, take general relativity. It's now extraordinarily well tested. I mean, things like a clock down here runs at a different rate from a clock up here. Well, it used to be this tower, and now it's from here to about there.
Sure.
I mean, these things are confirmed. These are really precise things that theory says, and experiments can be done, and they say, yes, this theory agrees with what we observe. Now, string theory is nothing like that. And in these postulated ideas about other universes around, there's nothing like that. So I can't quite see why we should consider those ideas as comparable with these wonderful things we do get from the physics we know.
Yeah. Sabina, do you think there's a residual element always that we can't get at?
So I was about to say pretty much the same as Roger. I think that underlying the scientific method itself, there's always the problem of inference, the way that Hume put it, or the way that Russell popularized it with his analogy to the chicken. The chicken is fed every morning at exactly 9 a.m. by the farmer, and it thinks that this is a law of nature until one day the farmer comes and chops off the head. So we have no telling that the laws of nature will still work tomorrow. This is just something which underlies the entire scientific methodology that we just assume to be true, but we can't test it itself, because how would we test it?
Yeah,
right?
Exactly.
But there is a somewhat more innocent example of something that we can't test, which is anything that is too rare to happen in the time that we measure it. An example may be proton decay, which is something that we've looked for a long time, but we still haven't seen a single proton decaying. But there are also other things, like, for example, the cosmological constant may not actually be exactly constant. It may very, very slowly change in a couple of billion years, but we'd never be able to test it. And that's an interesting example, I think, because what the cosmological constant does eventually determines the ultimate fate of our universe.
And do you think is there a place for proposing theories that we don't have evidence for, or that perhaps we can't have evidence for, but which somehow do function to hold our overall account of the world together in some way? Is there some purpose in that exercise, even if we think, well, actually, this isn't really science, it's something else?
I think there is a purpose in that. I think it's worth thinking. Certainly if you can have a scheme which is simpler in some respect, then it may not be testable, but on the other hand, it gives you an overall picture which is simpler than one which is different, but still not testably different. So it's certainly worth thinking about such things. But I think that it's really going over the top when one's talking about these multiverse ideas, which partly come from things about quantum mechanics which I think aren't correct, and someday we will, I hope, see what should replace them. But I can't quite see why we should be driven into this idea of all these universes coexisting. That I haven't understood.
So Michel, do you think there will always be a remainder of topics that we are not able to explain, which are untestable at some level?
Yes, there is a point at which all the known laws of physics collapse completely, and that's the Planck energy. The Planck energy is 10 to the 19 billion electron volts. That is a quadrillion times more powerful than our most powerful machine, the Large Hadron Collider. It is the point at which black holes and big bangs, all of that stuff takes place in the realm of the Planck energy, where Einstein's equations become useless. Einstein's equations diverge completely at the Planck energy. The laws of quantum mechanics, you have to have higher loop diagrams to control the divergences. It's a real mess. But that is the energy of the center of a black hole. That is the energy of the Big Bang. The most interesting places in the universe are beyond our mathematical ability because they exist at the Planck energy. In fact, the only theory which can operate at the Planck energy is string theory, but that's a whole other question. But the question you ask is there a point where the laws of physics as we know them break down? And the answer is yes. Two places, the center of a black hole and the beginning of the universe. That's where the Planck energy starts to come in. Wormholes dominate. All sorts of crazy things begin to happen. We have to think about the possibility of time travel, of gateways of the universes. It becomes a real mess at the Planck energy.
Yes, well, obviously the question is whether we take those descriptions seriously, isn't it?
No, I don't think we need to. No, I mean, the Big Bang is, well, I don't want to go into this because the Big Bang is a different story from the singularities in black holes. They're a completely different story. And to try and apply the same arguments to both is, in my view, quite wrong. I mean, I had the wrong view myself for a long time. So there's nothing against contemplating these things. I just happen to think, for what I regard as good reasons, that the singularity in the Big Bang are of an utterly different nature from the singularities in black holes. And this difference is extremely important. It leads to the second law of thermodynamics. It's part of the story. If they weren't different, we wouldn't have a second law of thermodynamics. I mean, these are things in physics that we see, very blatant things in physics, which if you trace them back, it leads us to the conclusion that what goes at the Big Bang is utterly different from the singularities in black holes. And therefore, to put them in the same category and saying string theory or multiverses or something is going to resolve that, I can't see that at all.
Very much so. Well, I'm afraid that is all we have time for. I think you'll all agree, an absolutely fascinating conversation.